So I would like to introduce our next speaker, Brian Coleman, G4NNS, who will be talking about the UK Meteor Beacon project, which is a collaborative project between the amateur radio and the radio astronomy communities in the UK. Now, Brian's been interested in radio from a very early age, particularly in VHF, microwaves, and radio astronomy. His activities have included hydrogen line observations to map the galaxy and to understand its motion as well as EME on the bands from 3.4 gigs up to 24 gigs. His interest in meteors was sparked when he noticed during open events in connection with the British Science and Engineering Week how all the visitors, and particularly the young visitors, were fascinated by real-time displays of radio echoes from meteors on 143.050 megahertz. So, and that's enough introductory, I think. So over to Brian for his talk on the Meteor project.
Right. Well, very good morning, ladies and gentlemen, and thanks for coming along to the talk. As our host has just mentioned, the UK Meteor Beacon project is a collaboration between the worlds of amateur radio and amateur radio astronomy. It has to be said that most amateur radio astronomers are also radio hams. What a surprise. The beacon is not primarily a meteor scatter or propagation beacon. It's really there to study what goes on as meteors enter the Earth's atmosphere. It's perhaps worth mentioning that it's reckoned that something like of the order of 10 tons of meteoric material enters the Earth's atmosphere every day. Most of it's not in one big lump, fortunately. It's in the form of little tiny specks of sand. You can see what the current status is of the beacon by going to the website, which is ukmeteorbeacon.org/status, gets you to that page. The beacon's been built with a lot of help from the amateur radio community. Andy, G4JNT, built the PA. Heather, M0HMO, has done a lot of the software. One of the guys at the Sherwood Observatory, Nigel, G7NJC, has been very helpful, and other members there. And with all this help, the beacon went live on the 14th of May and has been cheerfully operating since that time. An important aspect of this project, which I should mention is being supported by the RSGB Legacy Fund, is to use the interest that young folk in particular have in matters to do with space to introduce some interesting STEM-type projects that are perfectly doable from school or indeed from home with modest equipment to observe reflections from meteors as they enter from space. Now, the beacon is different in a number of ways from your normal propagation beacons in that it beams vertically upwards. It runs quite high power compared to propagation beacons, 75 watts it's currently running at, and it uses circular polarization. That's because if you're using a linear antenna to receive the echoes, and most people will, there is a potential for it to be, the echoes to be cross-polarized. So by illuminating the targets with circular polarization, a linear polarized antenna will be suffering no loss from the somewhat random polarization of the echo. Meteors burn up at an altitude of about 100 kilometers. I don't know whether I can get the pointer to work on here. Come back, all is forgiven, perhaps not. But the blue line on there shows the region at which they burn up, which is of the order 80 to 100 kilometers up. And the beam width of the antenna is such that it illuminates a region with a diameter of approximately 400 kilometers. The beacon's located at the Sherwood Observatory of the Mansfield and Sutton Astronomical Society, which is a reasonably central location. So it covers a large area of the UK, which until now has not been covered by any meteor beacons. There are meteor beacons elsewhere. For example, in Belgium, there's the Brams beacon and the VVS beacon, but there's no dedicated coverage for meteor events over the UK. And one of the objectives of the project ultimately is to compare the radio reflections with the optical observation by the Optical Meteor Observing Organisation, UK MON. You may have heard, and these organisations have had some success in looking at meteors entering the atmosphere and indeed predicting or calculating roughly where they're landing and actually picking up remains of ones that do actually make it all the way down to planet Earth. So it would be very good to coordinate with them. Phase one of the project has been to establish the beacon, which is on the air now, and you can tune to 50.408 and listen to it from, well, certainly anywhere in the British Isles. If you are closer than a few hundred kilometres to it, you're undoubtedly going to hear a direct signal, or you're going to hear aircraft reflections, because as it shows on that diagram there, the aircraft fly at about a maximum of about 10 kilometres, and echoes from aircraft will reach something like 400 kilometres, whereas echoes from 100 kilometres up will be receivable out to distances in excess of 1,200 kilometres. And there's some advantage in not being in the local coverage area of the beacon, because you're going to see a lot of aircraft and a lot of direct signals, which you're not really interested in. We're interested in the echoes from the meteors. Now, phase two of the project, which we're just moving on to now, is to design, build and deploy receivers to radio quiet locations at a suitable distance away from the beacon, to stream their data and make it accessible to anybody who's interested in the first instance, but then move on to other more scientific studies, of which I'll touch on later in the talk. In principle, anyone can build a receiver. It could be something simple like a FunCube dongle and a suitable antenna. We quite like the Moxon antenna because at 6 meters it's reasonably compact and it's robust. If you're within about 200 or 300 kilometers of the beacon, it pays to point the antenna up towards that point 100 kilometers above Mansfield, and that's quite a useful trick because it helps cut out some of the ground-based man-made interference, which is good news. So anybody can build a receiver, but we're going to produce a design specifically to form a network of receivers that will stream their data ultimately via a central server, so anybody can access any of the receivers, which will be dotted around the country, hopefully many of them in nice quiet sites. I'll come back to that, and at a suitable distance from the beacon. Individuals will be able to build their own receivers to the design we produce. The UK Radio Astronomy Association has a track record of producing circuit boards and so forth, which will be made available to anyone who wants to build a receiver, and if they wish to, they can join it into the network and we will capture the data. More of that later. It's really rather similar to a web SDR, except that we're going to be looking at a very narrow slice of the spectrum. We're only interested in the meteor echoes. Now, this is what meteor echoes look like. Actually, I could really do with a pointer here. I don't know if you can see at the bottom of the trace, there's a little horizontal line, almost horizontal line at the bottom of the trace. That's known as the head echo. Let me see if I can persuade. Yes, I seem to remember. Got it. That little bit there is the head echo. And you notice that it has changing frequency. That's the Doppler shift from the head echo as the geometry between the transmitter and the receiver and the meteor is changing, and also as the meteor is decelerating due to friction, which is what generates the heat, which is what generates the ionization, which causes the reflection. So that's an important point, and I'll keep coming back to it. That's the head echo. This we know as the tail echo. This particular shot was one of many, many that I've made. My location is about 200 kilometers away from the beacon, so I do see some direct signal from time to time. I also see aircraft reflections, but this one's nicely out in the clear. This was made using SDR console as the software, but pretty well any of the other ones can potentially do the same sort of thing. The SDR, which we are starting to use for the Receive project, is actually an RSPDX. That's what we are thinking of basing the system on. It's not cast in concrete yet, but that's the prime runner at the moment. For studying individual meteor events, which is what we want to do, I prefer this kind of display. You will see from astronomers, a lot of them use a spectrum lab set up to show the waterfall horizontally, and usually with a very extended time scale, so you see lots of events, and you see virtually nothing of the head echo, which I find a bit difficult, because it's the head echo that is the really interesting bit, I think, as far as meteors are concerned. So here's another fairly typical echo, and we describe, as I've already alluded to, this as being in two parts. The head echo, which exhibits very rapidly changing Doppler shift. That's the horizontal line here. And they last typically of the order of 100 milliseconds, maybe a few hundred milliseconds at most. They are not what is generally used for meteor scatter. They're too short, and the rapidly changing Doppler shift would not make life very helpful for communications purposes. They're described as over-dense echoes, referring to the fact that the electron density of that bit of plasma that's, if you like, following the meteor down, it has got a high electron density. And the other component we call the tail echo. It's really nothing of the sort, but is the bit that we use for meteor scatter communications, and this is known as an underdense echo, and you notice that it exhibits very little Doppler shift, and what Doppler shift it does exhibit is due to the wind speed at the altitude where the ionization has been created. Here's a head echo exhibiting a large range of Doppler shift. You don't very often see these, but you do see them from time to time. In this case, the path from the beacon up to the meteor and back to the receiver was closing at about 21,000 kilometers per hour at the start, on the right-hand side, over here, and by the time it disappears, it's receding at about 10,000 kilometers per hour. And most of that change is due to the geometry changing as the meteor sweeps across the sky, but also because the meteor itself is decelerating. Thinking about the geometry of an echo, you see that the Doppler shift observed depends entirely on the geometry. If you take this case, we've got a transmitter here, and take receiver B, that path at this particular instant here is extending, and this one is reducing, and indeed if those two angles are equal, there will be zero observed Doppler shift from that particular receiver. On the other hand, if you're observing from here, the path, I think that angle there is very nearly 90 degrees, so there'll be no Doppler shift or little Doppler shift on that path, but a lot of Doppler shift on that one because the meteor is approaching the transmitter. So that kind of underlines the effect of the geometry on the Doppler shift that you're going to measure. Now, the primary objective of this project, or a primary objective, is to collect enough data of sufficient quality that we can count and classify meteor events and learn a bit about the mechanisms that are going on, as the meteors burn up, and there are quite a lot of different views. It's been very interesting attending a couple of the lectures today that have shed more light on the processes that are going on, particularly Chris's talk and also John Renault's talk. These meteors are burning up at about 100 kilometers. It's the ionosphere. There are lots of ions about. There are lots of processes going on, and we are a long way from fully understanding them. So the objective is to collect as much data as we can and see where it leads us. And to do this, we want to analyze the data and analyze the echoes and classify them accordingly. And here are some simple things that we might look for. Did the echo have a head? They don't always have a head. The echo might have been from ionization caused by some other process. Who knows? Or it may just be that we didn't see the head for some reason. Interesting to know the amplitude and spectral spread and duration, and the Doppler shift, maximum and minimum Doppler shift, and so on. And this is all data that we can quite relatively easily collect with fairly simple software-defined radio techniques and without a very big bandwidth. We're looking here, probably the bandwidth of the receiver will be a lot less than 20 kilohertz. We might settle on 20 kilohertz just so we've got plenty of redundancy, if you like. Now, one of the ambitions, and I emphasize this is an ambition, it's not strictly part of phase 2 of the project, is to find or to correlate observations from different directions, to pick an instant where a number of receivers are seeing the head echo, and to measure carefully and accurately the Doppler shift at that instant. If we can do that, we can potentially triangulate the location of the meteor and its trajectory. And this is very interesting, not just because people want to know where, if it's going to land on planet Earth, where it's going. That's quite interesting. But what's more interesting to astronomers is, where did it appear to come from? Is it part of a regular meteor event? And we can then calculate what is known as the radiant. The radiant, as we know with the meteor showers that we're all familiar with, the Perseids appears to come from Perseus. They don't really, but that's the part of the sky they appear to be emanating from, and the Leonids from Leo, and so on and so forth. It would be really interesting to discover, for example, a new radiant for minor meteors that nobody's noticed before. And if we're collecting bulk data, this is the sort of thing that might happen and might be, and is certainly of great interest to the astronomy community. This is another fairly typical echo from GB3MBA with a short, very short head echo. I think you can just about make it out there, and a very long tail echo. And this one, actually, my notes say over 5 seconds. It's well over 5 seconds, and that's the sort of tail echo that you could have a complete QSO on one of the digital modes with no trouble at all. But the head echo, as you see, is very short and not much use for communications. Here's another fairly fuzzy-looking echo, which doesn't have a head, and the question is, was that because we couldn't see it? That particular observation didn't see it. If we were looking at it from different directions, would others see a head? I.e., is the head echo directional in some way, shape, or form? And that will be of considerable interest. I'd like to introduce 3 possible explanations of the processes that give rise to meteor echoes. And these are not necessarily things I believe in. In fact, after listening to the other lectures, there are other explanations which people fervently believe. But the point I'm going to try and make here is to explain very briefly what the explanation is, and to suggest what that explanation would predict. so that we can then compare our observations with the predictions of each of the explanations and see which ones appear to be valid and which ones are not. The first explanation, which is, I think I've heard this mainly from the astronomy community, is that you've got the fast-moving head of the meteor reflecting radio. Echoes from it show the rapidly changing Doppler shift that we see in the head echo. Probably that reflection is more or less isotropic, and that at some point the ablation material from the meteor somehow explodes and leaves a cloud of ionization behind it, which is the tail echo. I think one of the things that would predict is that we would not see many head echoes that continue past the formation of the tail echo. So one possible prediction, if that explanation is right. Here's a much more complicated one, which is from Peter Martinez, G3PLX, and it's based on modeling. I'll leave you to read it in peace, and I'll just talk about the punchline, but it is based on modeling. So the punchline of this, as far as what it might predict, is that this predicts that the head echo will be isotropic. It won't be directional. So something to look for when we start analysing the data from phase 2 of the project seriously. This explanation, which is based on observation, is very likely an oversimplified view, is that the head echo is basically a thin trail behind the meteor. Bear in mind, most of these meteors are no bigger than a speck of sand. That you've got this overdense, highly ionized tail, which will behave like a piece of wire flying through the sky. And this would predict that a reflection off the head might be directional, depending on the length of the wire. It certainly won't be a big signal when you're viewing it head on, or either the transmission is illuminating it head on, or you're receiving it more or less head on. So there will be a degree of directionality, and possibly it will be polarized if it's like a piece of wire. So those are the predictions from that explanation. The tail echo, the thought with the tail echo is that the meteor, with its very hot, highly ionized tail, is passing through an area of the ionosphere, the clue's in the name, which is already more or less ionized, and perhaps a very hot ionized object passing through it causes a volume to become sufficiently ionized to become reflective to radio for a time, a variable amount of time afterwards. But if that were, in this particular case, that would say that sometimes the meteor would pass through and continue on without having kind of exploded and disappeared. So we'll be looking for that as we analyze the data. So just recapping on that, explanation 1 suggests the head echo reflects isotropically, not directional. We might expect the explosion of the head would would cause the head echo to stop abruptly at that point, and we do see that quite often. Explanation 2 predicts the head echo reflects isotropically, and that the tail echo should form shortly after the start of the head echo. So where we saw that line, the very nearly horizontal line, one might expect that the tail echo would form shortly after that has started. So you would sometimes see an overlap of the head echo and the tail echo. Haven't seen that. And the third explanation predicts that the head echo may well be directional. So there are three possible explanations and three bits of the data that we'd be interested to capture so that we can put the theories, if you like, to the test. I was hoping I would avoid using the word theory. I think that dignifies them with a little bit too much science. They are possible explanations, and there are certainly others. Coming back to the diagram of phase 2 of the project, we aim to deploy these receivers to form a network that can stream their data from observations from a variety of different directions so that we can clear up the question of are head echoes directional or not? Are they isotropic? And in order to do this, to deploy these receivers, we want to find radio quiet locations dotted around the countryside. And here perhaps we have an advantage that working with the astronomy community, some astronomy societies have quiet, dark observing sites, and increasingly some of them have power and the internet to these sites because they're looking at remote-controlled optical telescopes, and we can hopefully persuade some of them to host the receivers. The receivers will be quite simple pieces of kit, which I'll go on to show, and this, I think, indicates the general setup. So the receivers will ultimately or to begin with, they'll stream to the development team so that we can look at the data we're getting and we start to think about how we're going to analyze the data. But as the project progresses, they will ultimately stream to a central server, which will do some analysis and will provide access to for multiple users. Anybody wanting to do meteor observations will be able to access any of these receivers and collect and analyze the data as they see fit. So this is a simplified block diagram. Initially, we're producing 3 or 4 receivers to be put to start the network rolling. But once we've done that, I know individuals will want to build their own receivers, and where practical, if their QTH is reasonably electrically quiet and they're happy to have it connected to the internet, individuals will build their own receivers. And then there'll be the individuals who don't want to join the network but might quite like to build a receiver, and they're very welcome as well, of course. At present, the plan, and we're just starting, the design team is just forming now, and we're taking input from all sorts of different directions, but the timing, the plan is to base the receiver on the RSPDX, as I mentioned earlier, and a Raspberry Pi, as long as we can get them. And this is roughly the format. It will consist of a GPS-locked reference, because we want to make very accurate Doppler measurements. The transmitter is GPS locked, so very important we have good frequency accuracy. We're also ultimately going to want very precise timing, preferably a millisecond timing. And the current thinking, there's lots of ways of, well, I say lots, there's several ways of doing it, but the current thinking is that this will be done with a GPS-derived time mark, perhaps once a second, maybe once every 10 seconds, which will be input into the front end of the receiver. That is so it can take account of the latency through the receiver as well as the latency across the internet. This is the current thinking. It may change. These receivers will have the option of a local display, a waterfall display like the ones I've shown you earlier, because if you're hosting one of these at home or at a school or somewhere or in a astronomy club, they might like to see what's actually happening in real time, but it's not necessary. It'll be an option. The receiver will be an option. So to achieve our later ambition to triangulate meteor events, and this is beyond phase 2 of the project. We need that very precise timing, and as I say, to take account of the latency through the receiver and over the internet. And here is a proof of concept where we're generating a little burst. They're actually 15 millisecond bursts of 1 kilohertz lower in frequency than the Meteor beacon on 50.407, and you can see them on the left there. Those are ticks which could be synchronized with UTC from the GPS receiver. That's one way of doing it. That's how we plan to get that precision timing. As earlier mentioned, this is a cooperation between the world of amateur radio and the world of radio astronomy, and these science objectives are ones that were listed from the radio astronomy community. Some of them may sound a bit slightly unusual to us as radio amateurs, but nonetheless this is their list. They want to make accurate meteor counts, assist in identifying new meteor streams and detecting outbursts in known ones. They would like to cross-correlate with the other meteor beacons that don't cover the UK, BRAMS and so on, and the Graves beacon, which you may well be familiar with. I should just mention the Graves beacon on 143.050 is an interesting starting point, but it doesn't provide realistic coverage over the UK. It's stuff south of Dijon, basically. But it's certainly good to demonstrate to anybody meteor pings, because you've only got to tune straight to it, and you'll be seeing pings within seconds, and Starlink satellites and everything else that's up there whizzing by. But the propagation is so different on 143 megs that don't get too strung up about it. At 50 megs, we've got all the wonderful things that happen on 6 meters to contend with as well. High noise levels, sporadic E, you name it. They would like to cross-correlate with UKM on the video camera network. But of course, our system will work 24 hours, 24/7, and theirs only works on clear nights. So that's useful. And they'd like to also like to compute the trajectories and narrow down the landing locations and calculate the radiance from which they appear to have come. And they go on with a few more objectives that they're interested in. The article which you may have seen in Radcom this month is just now published in the Journal of the British Astronomical Association, so I'm expecting quite a lot of input from the astronomy community sort of any time soon. I think what I've got here is just a few more examples of the typical kind of meteor you see. Here is one little head echo which continues past the formation of the tail echo, and a little tail echo there that's probably 2 or 3 seconds long, perfectly adequate for meteor scatter contacts and so forth. And you can see that the time scale obviously is the vertical here, and that head echo probably lasted 100 milliseconds or less. And this is the sort of thing that, as a STEM project, somebody could put up a pretty simple antenna, FunCube dongle or something like that, and at a school they could start receiving meteors. And here's another one that without a head echo. Was it a meteor? Was it something else? Who knows? It's the ionosphere. So, would you like to contribute to the project? Either become an observer using your existing equipment, and perhaps coordinate observations. We haven't got to a stage where we've got anybody coordinating the observations yet. We're working on it. Would you like to build your own receiver and join the network when the design is available, which I would predict is probably maybe at the back end of the first half of next year. We're working on it now. I would think probably by May or June or something, we will have the receiver design firm enough for people to actually build their own. Host one of the network receivers if you've got a quiet location. Most of us transmit, so maybe we don't have quiet locations. But maybe you can find the local astronomy society and fire them up. Help with installation, maintenance, coordinate observation, as I already mentioned. And the last thing, which I think is very important, and we really want to work on this, and was one of the reasons why we got quite reasonable funding from the Legacy Fund, is to use this as a tool to encourage STEM projects with schools and so on, building on the interest that they have in space. One thing I forgot to mention, if I just go back to one of the Meteor echoes there, anyone will do. The other day somebody said, well, how long do you have to wait before you'll see an echo? In my case, with my setup, which is nothing particularly special, RSPDX and a Moxon antenna, 200K from the beacon, and I point it up a little bit so that it's notionally pointing at the 100K above Mansfield, and also it slightly nulls out the electric fence in the next field, which is very helpful. And I said, well, you know, even outside a meteor shower, you're going to see about 2 a minute. And they said, no, that can't be right. I emphasized that they are like buses, but I said, look, I have a number of recordings, 5-minute random recordings that I've made, and we played one there and then, and sure enough, it was about 2 a minute. So you don't have to wait long to see them. And if anybody would like to play those recordings, you can replay them on SDR console. I'll put the address where you can find them. They're on my web page somewhere, but they're not kind of public, but I'm very happy to point anybody at them if they're interested. So that about wraps it up. Over to you. Any questions?
Thanks, Brian. Are there any questions? And just put your hand up and I'll bring you the microphone.
Thanks, Brian. Mike, G4CDF. What do you define as a suitable radio quiet location? Would a normal location in suburbia do, pointing upwards, or is it got to be quieter than that?
Some people seem to be lucky in suburbia and some less so. And I think perhaps I should have included a slide on this. Probably the first thing you should do is sling up a dipole, if you haven't already got a 6-meter antenna, and look at the increase in noise versus a resistor, 50 ohm resistor. And I have a number in mind. If it's much over, if it goes up by more than about 10 dBs, then you're not a quiet location. If it's less than 10 dBs, you're okay. If it's less than 6 dBs, you're a very quiet location. So, yeah, it's something to check.
I just wondered how good the Moxon was at Sorry, I just wondered how good a Moxon was at removing the noise from everything around it if you were pointing upwards.
Yes. I think I would recommend, ordinarily I would recommend that the Moxon, if you're within 200 kilometers, that you point your Moxon almost straight up, and that will definitely help. But as the angle goes down, I mean, I'm 200K from the beacon. I think, well, actually, the angle that I point up by was determined by a clamp that was in the junk box, and it's about that sort of angle, so what should we say, 30 degrees or something. And that definitely produced a reduction in electric fence noise, and especially compared to my 3 or 4 element beam, which is horizontal, where the fence noise is awful. If you're further away, in a perfect world, I would suggest you're beaming horizontally. You've got to beam horizontally, and more gain would be helpful because these signals are not terribly strong. If we could run a couple of megawatts, they would be a lot bigger. But unfortunately, the electricity bill is just too much, and Ofcom wouldn't like it. So yes, But I have noticed that moving the antenna around, even in my relatively quiet rural location, you can find spots that are a lot quieter than others. And you know, if you are just using a dipole, putting it end on to the worst noise is a good start.
Over there. Just let me bring the microphone to you.
Cheers. Another Brian, G4BIP. A point actually, I suppose, about the aerial is don't put it too high. If you keep your antenna fairly low, you'll avoid picking up too much of the terrestrial-based stuff, and I do that quite a lot for satellites. You kind of want to point up. The question was, I've done a bit of listening to the Graves radar, and some of the head echoes that we've seen coming through there seem to split. Now, I was confused as to whether this was actually a sign of the meteor actually breaking into fragments, and each fragment then having its own Doppler trace, or is it multipath propagation coming from different routes to my aerial?
Yeah, I'm certainly not a specialist with Graves, but remember, Graves scans round in, 2 seconds, or however many steps, it goes from east through south to west. And that must account for some fairly strange things. And also, I don't know where you're located. I'm located in North Hampshire. And if I beam at Graves, I virtually get a direct signal all the time by some propagation mode. I'm not clear what it is. All these strange propagation modes, be they on 6 meters or on 2 meters, albeit that they're quite different, I refer to them as propagation mode of the day.
Evan, M0TJU. Thanks for the talk. They're very interesting. Just wondering if has anyone sort of tried correlating, crunching the numbers, using FSK 441 or MSK 144 logs, putting those together and putting visual observations together to get an idea of this sort of stuff? Because you give your locator each time, and presumably there's a particular geometry that has to be to get that path. So could you calculate it from that? Yeah,
I think that would be a very interesting thing to do. If somebody's got the time, patience and knowledge to put the software together to draw it all together, I would be amazed if we didn't discover anything from it. So yeah, why not?
Any more questions? We have time for a couple more probably. Looks like we're all done for the time being. I suspect Brian will be around a bit. Oh, no, sorry. Let me just bring the microphone across.
Sorry, 2E0 HXM. What does the nature of that outreach help look like? What's actually been looked for there, and what are the characteristics of those who can help, and how has it been coordinated?
Right, it's a very good question. I think we've been so focused on building the beacon and getting phase 2 going that although we know that a major objective is the outreach side, we haven't got an outreach champion yet. We're definitely looking for somebody. I mean, it could range from setting out what a project consists of, like make a dipole, get hold of a receiver, be it a FunCube dongle or whatever, right the way through to actually liaising with a school or a college, or providing guidelines. It's an area we need to develop. We need to find a champion for that, and it's on my list of my to-do list, basically.
Thanks, Brian. I think we have no more time for questions, I'm afraid, although Brian will be around, I'm sure, maybe downstairs a little bit later. So can we all thank Brian for an amazingly interesting talk.
Thank you.